Archimedes of Syracuse, a Greek mathematician, physicist, engineer, astronomer and inventor from the ancient city of Syracuse, once said, "Give me a lever long enough and a fulcrum on which to place it, and I shall move the world." In fact, the first designs of propulsion go back thousands of years ago. However, Archimedes' original displacement screw had nothing to do with ships and hydrodynamics. It was firstly invented to displace grains and cereal crops. But it was soon realized that the same system could be used to displace liquids, providing an effective way of causing a flow of material. When the Archimedes screw is submerged, a thrust is created by the displacement of water. And this actually takes us back to the famous third law of Newton. For every action, there is an equal and opposite reaction. This expression is not always evident, but it is the essence of everything that moves through the world. In fact, as you are going for a walk, or maybe running while doing some cardio, your feet are there to push back against the road, to move you forward. Meanwhile, up to the 15th century, exactly on 1493, one of the greatest masters in history, Leonardo di Ser Piero da Vinci, have also confessed sketching some futuristic propulsion designs, as he was obsessed about figuring out the science behind aviation flight. But concerning ships, the propeller has been proven to operate by pushing or pulling forward, holding a mass of water backwards, propelling a big heavy ship, which makes in evidence the theory of the Swiss mathematician and physicist Daniel Bernoulli, who came to state on the 18th century that an increase in the speed of a fluid occurs simultaneously with a decrease in pressure or a decrease in the fluid's potential energy. In fact, Bernoulli's principle causes low pressure in front of the propeller, caused by the water being pulled into the propeller, and a high pressure behind, due to the water rushing from the propeller, creating force from it. Let's try to sketch the situation to better understand the concept. As the propeller starts operating, turning clockwise or counterclockwise, the speed of the fluid is increasing, up being pushed by the propeller, which creates a phenomenon of a higher pressure compared to the area next to the shaft, as the water has been pulled into the pressure. And there's where the Newton's law comes into play. The action is the propeller applying the force backwards, and the reaction is the ship moving forward. The first person to successfully utilize the screw propeller familiar to us today was Isambard Kingdom Brunel, who developed a six-bladed version in 1847, fitted in the Great Britain ship, the first screw-propelled iron vessel to cross the Atlantic. Since then, the Brunel model changed actually very little, reinforcing the ingenuity of this revolutionary device. That is where the world has discovered multiple propellers types and designs. But is there any standard propeller geometrical reference? The 10th International Tone Tank Conference, known as ITTC, initiated the preparation of a dictionary-like nomenclature of ship hydrodynamic terms, which was completed in 1975. ITTC proposed in fact a right-handed rectangular Cartesian system. For propeller geometry, it is convenient to define the local reference frame, having a common axis, such that x and xf are coincident, while yf and y, as well as z and zf, rotate relative to the oy and oz fixed global frame. The line normal to the shaft axis is called either propeller reference line or directrix, and the line formed by the intersection of the pitch helices and the plane containing the shaft axis and reference line is called the generator line. Now let's look deeper into the helix's geometry. The side of a propeller blade which faces downstream during a head motion is called face, while the side of a propeller blade which faces generally the direction of a head motion is usually called back. While the propeller is rotating the edge first in water, we have what is called leading edge. But when the propeller is rotating the edge trailing the leading edge, it's called trailing edge. Now, you might have heard multiple times in the hydrodynamic engineering lexicon the term pitch, which is now playing a fundamental role in our propeller analysis operation. So let's take time to have a look at it. Let's now consider a point P lying on the surface of a cylinder of radius r, which is at some initial point P1, and moves as to form a helix over the surface of a cylinder. The propeller moves forward as to rotate, and this movement creates the helix. When the point P has completed one revolution of helix, that means that the rotation angle is now phi equals to 360 degrees, or 2 pi. The cylinder then intersects the xz plane and moves forward at a distance of p. The distance moved forward by the helical line during this revolution is p, and the helix is given by the formula theta equals to the inverse tangent of p divided by 2pr, where p is the pitch and theta is the pitch angle. When t equals to 0 seconds, which means that the propeller is still at rest and not pushing water, the pitch in that case is equal to 0. The pitch of the propeller is permanently fixed and cannot be changed during operation. The blade pitch of a propeller can be defined as the displacement that a propeller makes for every full revolution of 360 degrees, assuming no slip. But what is even slip? Slip is the difference between the actual and theoretical travel through the water. Let's take an example. Now, if a 20-inch pitch propeller actually advances a 17-inch revolution in the water, it is said to have a 15% slip, as 17 inches is 85% of 20 inches. Now, while building propellers, there is a very important fact to consider, which is the materials of construction. You need to understand that not only for propellers, but in today's technological age, constructions of materials play an important role, as no field of engineering would be complete without these materials. The materials of construction industry is a significant contributor to the international economy, and its outputs influences deeper both rate and quality of the construction work. Generally talking, the materials used for marine structures need to withstand seawater on the long term, and therefore need to be corrosion resistant, such as aluminium and manganese. But aluminium bronze is generally preferred due to its lighter weight and good strength properties. And so is the case of the 2 and 3 blade propellers, while a 4-blade propeller is typically made of stainless steel, which is an alloy steel known to be heavier and stronger than aluminium, known also for exhibiting corrosion resistance properties due to the formation of a very thin layer of chromium, Cr2O3, on its surface by 10.5% as a minimum amount. Now, is there any propeller types classification methodology? Propellers are indeed typically classified regarding 2 main factors: number of the blades and the pitch of the blade. Propellers' blades may vary from 3, 4, 5 to 6 blade propellers. The propeller efficiency will be highest for a minimal number of blades, but to achieve strength factor and considering the heavy loads by the ship, sea, and weather, 2-blade propellers would not be enough. In such cases, 5 to 6 blade propellers are used despite the higher manufacturing costs, as they promote less vibration than the 2 or 3 blade propellers and have better holding power in rough seas. But the most commonly used for cruising boat types are the 3 and 4 blade propellers, as they give good high-speed performance, better acceleration, as well as better strength and durability properties. Propellers like the 4-blade propeller provides a better fuel economy than all the other types. On the other hand, the blade pitch can be classified into what we call FPP and CPP. The FPP refers to the fixed pitch propeller. In fact, the blades of an FPP are permanently attached to the hub. The position of the blades and those of the pitch are permanently fixed and cannot be changed during the operation. They are robust, reliable, lower cost than CPP, and they have good maneuverability. While the CPP refers to the controllable pitch propeller. It is possible to alter the pitch by rotating the blade about its vertical axis by means of mechanical and hydraulic arrangement, which helps in driving the propulsion machinery, and constant load, by altering the pitch to match the required operating condition. Now, all this information we gathered about the propeller's geometry, materials of construction as well as the classification methodology takes us to our last part of this video, which is to finally understand how propellers actually work as a part of the ship. Marine propellers achieve propulsion by using their angled blades in order to generate thrust. The same concept we can notice for airplanes in order for them to achieve lift. The action preceded by propellers is analogous to the action of swimming accomplished by humans, pushing the water down and back. Also, the propeller is pushing the water down, which will automatically create a water current behind the blades, leading to a pressure differential situation between the two sides of the blade, positive pressure and a negative pressure. The positive pressure is created by a pushing effect of the underside of the propeller blade, while the negative pressure is due to the pulling effect created by the top side of the propeller blade. But of course, it's clearly undeniable that the propeller is not proceeding its mechanism solely. A whole linked mechanism is playing an instrumental role for the successful work accomplishment. In fact, the propeller is only a part of a long handle called the shaft, which is directly connected to the main engine, which makes the propeller both, if we can say, dominant and subordinate, pushing as well as being pulled through the water. The propeller can produce two types of thrust, axial and transverse. The axial thrust produced by the propeller against the water acts on the thrust bearing of the intermediate shaft, which makes the ship move forward and astern, while the depth of the motion of a propeller, thanks to the transverse thrust, is caused by the interaction between the hull, the propeller, and the rudder. It is the tendency for a forward and astern running propeller to move the stern to the starboard or port direction. See you on the next video.